Now in this lecture I'll answer two questions. In the first question we find out the area of this pentagon ABCDE, and in the second question we find out the area of this gun shape. So we start with the first question. In the drawing we have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interior angles. This is pentagon ABCDE. It has 5 sides: 1, 2, 3, 4, 5, and 5 interior angles: 1, 2, 3, 4, 5. So in the drawing we have pentagon ABCDE. Those two angles are both right angles. Side ED equals to 1 unit in its length, side EE also equals to 1 unit, side BC equals to 1 unit, side DC equals to X units in its length, and side AB also is equal to 1 minus X units in its length. Again, our task is to find out the area of this pentagon ABCDE. So first of all, we join points A and B together by a straight line. And we join points C and C together by a straight line. In the next step, we'll extend side BA in such a way that the extended side, the extended part, will be equal to X units in its length. We define this point M. So according to our construction, AM equals to X units in its length. PA is one side of pentagon ABCDE, and therefore it is absolutely a straight line. We extend the straight line BA by straight line, the result BM must be also a straight line. We extend the straight line by straight line, the result must be a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is right angle, plus this missing angle. In total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will join points E and M together by a straight line. By joining points E and M, we created the right angle EAM. So in the next step, we prove that those two right angles can go into each other according to side angle side rule. So later on, we have to prove that the right angle EAM and went to the right angle EDC, this right angle EDC, according to side angle side rule. Again, we have to prove that the right angle EAM can go into the right angle EDC according to side angle side rule. So what those two right angles can go into each other? First of all, those two sides are both equal to x and therefore they are equal to each other. So here it is the side MA, on the right hand EAM, and it is equal to this side the DC, on the right hand EDC. And again, side MA on the right hand EAM is equal to side DC on the right hand EDC. They are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle EAM. In the right hand EAM, it is equal to this angle, that is actually angle EDC. In the right hand EDC. And again, if you found out that angle EAM in the right hand EAM is equal to angle EDC in the right hand EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. So here this is side EA. In the right hand EAM, it is equal to this side, that is side ED. In the right hand EDC. They are both equal to 1 and therefore they are equal to each other. Again, side EA in the right hand EAM is equal to side ED in the right hand EDC. They are both equal to 1 and therefore they are equal to each other. So if you prove that those two sides and the angle that is included between those two sides, that is the right angle, in this triangle EAMA are correspondingly equal to those two sides, and the angle that is included between those two sides, that is also right angle, in this triangle EDC. And therefore, those two right angles can go into each other from the side angle side over. So triangle EAM converge, this is the sign of converge, to the right triangle EDC according to side angle side rule. And again, we should follow that those two sides and the angle that is included between those two sides in the triangle EAM are corresponding equal to those two sides and the angle that is included between those two sides in the right triangle EDC, and therefore those two right angles can go into each other according to side angle side rule. And for the fact that those two right angles can go into each other, we derive two things. The first thing that we will derive is that they have the same areas. Any two triangles that can go into each other, they must have also the same areas. That is to say, the area of this triangle EAM is equal to the area of this triangle EDC. And again, the area of triangle EAM is equal to the area of triangle EDC because they can go into each other. And the second thing that we derive from the fact that those two right triangles can go into each other, that side EM of the right triangle EAM is equal to side EC of this right triangle EDC. EM equals to EC. This is side EM, this is equal to side EC. So if you know, side EM is equal to side EC. Why side EM is equal to side EC? Those two sides are equal to each other according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles congruent to each other, and therefore those two corresponding sides must be also equal to each other in their lengths. So this is the right green triangle EAM. And this is the right green triangle EDC. I shall found out that those two white green triangles have the same areas. So if you define the area of this green right triangle EAM as Z, that is to say, after green right triangle EAM is equal to Z coincident size, then the area of this green right triangle EDC must be also equal to its size must be also equal to Z coincident size because they have the same areas. The next step, we find out the graph of line segment MB. From the drawing, it is very easy to see that MB in total equals to MA plus AB. So you know, MB equals to MA plus AB. So MB equals to MA. MA is X plus AB. AB is 1 minus 6. So in total, MB equals to X plus 1 minus X. X minus X is 0, so we're left only with 1. In total, we should know that MB equals to 1 unit in its length. So side MB is equal to 1 unit in its length. The next step, we prove that triangle MEB can go to this triangle EBC according to side rule. Okay, again, we prove that those two triangles can go to each other according to side rule. So right now we have to prove that triangle MEB can go into this triangle EBC according to side rule. So why those two triangles can go into each other? First of all, we already found out that EC equals to EM. Again, EC equals to EM. Or EM equals to EC. So side EM or triangle EMB is equal to side EC or triangle EBC. And again, I should remember that side EM or triangle EMB is equal to side EC or triangle ECB. In addition, side MB or triangle EMB equals to 1 and it equals to side BC of this triangle EBC, that is also equal to 1 unit in its length. So MB equals to BC. is again side MB of triangle MEB is equal to side BC of triangle EBC. They are both equal to 1. They are both equal to 1 and therefore they are equal to each other. And finally, side EB is a common side that belongs to both triangles. It is very easy to see from the drawing that side EB belongs to this triangle BEC and side EB also belongs to this triangle BEC. So side EB equals to itself. It's a common side that belongs to both triangles. EB equals to itself. It's a common side that belongs to both triangles. So if you found out that all the three sides of this triangle MEB are corresponding equal to all the three sides of this triangle BEC, and therefore those two triangles can go into each other according to side also. Write it down. If you found out that, and therefore those two triangles can go into each other according to side one. Triangle MEB can go in. This is the side of can go to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we realize that they have also the same areas. So there are this side EMB is equal to the area of this triangle EBC. And again, I should know that the area of triangle EMB is equal to the area of triangle EBC because they can go into each other. In the next step, we find out the area of this triangle MEB. We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this triangle MEB must be equal to the base MB times the height AE over 2. And again, if you don't know that the area of triangle MEB is equal to the base MB times the height AE over 2. We have already found out that MB equals to 1 times AE. AE also equals to 1 divided by 2. So in total, the area of triangle MEB is equal to 1 times 1, that is 1 over 2. The area of triangle MEB is equal to 1/2 square units in its size. So you can write here that the area of triangle EMB is equal to 1/2 square units in its size. And from this equation, 1/2 equals to the area of triangle EMB equals to the area of triangle EBC. We derive that the area of triangle EBC is also equal to 1/2 square units in its size. Those two sides are equal to each other. So the area of triangle EBC is also equal to 1/2 square units in its size. What is the area of this big quadrilateral EMBC? The area of quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of this B quadrangle EMBC must be equal to the area of those two shapes that it consists of. You see that quadrangle EMBC consists of this shape that is triangle EMB, and also this the second shape that is triangle EBC. So the area of the B quadrangle EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of triangle EMB plus the area of triangle EBC. We already found out that the area of triangle EMB equals to 1/2 plus the area of triangle EBC that is also equals to 1/2. 1/2 plus 1/2 is 1. So here in total found out that the area of the big quadrangle EMBC, in total it is equal to 1 square units in size. But we can look in quadrangle EMBC in another way, and we'll find out that quadrangle EMBC consists of two other shapes, and therefore the area of quadrangle EMBC must be equal to the sum of the areas of the two other shapes that it consists of. Actually, the big quadrangle EMBC consists of this right triangle EMA, and it also consists this quadrangle ABCE. Therefore, the area of quadrangle EMBC must be equal to the sum of the areas of the two other shapes that it consists of. That is to say, it must be equal to the area of the green triangle EMA plus the area of this quadrangle EBCE. So written down, we found out that in total the area of the big quadrangle EMBC is equal to the area of the green triangle EMA plus the area of this quadrangle ABCE. In the end, we found out that the area of the big quadrangle EMBC must be equal to the sum of the areas of the two other shapes that it consists of. So it must be equal to the area of the green triangle EMA plus the area of quadrangle ABCE. And from this long equation, it's very easy to see that those two sides are equal to each other. That is to say, one equals to the area of the green right triangle EMA plus the area of quadrangle ABCE. So at the done, we found out that one equals to the area of the green right triangle EMA plus the area of quadrangle ABCE. Turning to this long equation. But according to our definition, there are this green right triangle EMA equals to z square units inside, so we can substitute the area of triangle EMA by z. We get that 1 equals to z plus the area of quadrangle ABCE. So again, in total, we found that let 1 equals to Z plus the area of triangle ABCE. 1 equals to Z plus the area of quadrilateral ABCE. Our task is to find out the area of this big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, the area of this big pentagon ABCD must be equal to the sum of the areas of the shapes that it consists of. The big pentagon ABCD consists only two shapes. The first shape is the green right triangle EDC, and the second shape is quadrilateral ABCE. And therefore, the area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this green right triangle EDC plus the area of this quadrilateral ABCE. And again, we should find out that the area of the big pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. It consists only those two shapes and not anything else. And therefore, the area of pentagon ABCD must be equal to the area of the first shape, that is the green right triangle ABCD, plus the area of the second shape, that is quadrilateral ABCE. That the area of this entire EDC equals to Z. Z corresponds in size. So we can substitute the area of triangle EDC by Z. Which is equal to Z. Plus the area of quadrilateral ABCE. So in total, we should find out that the area of the big pentagon ABCDE is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABCE equals to 1. So we can write here that Z plus quadrilateral Z plus the area of quadrilateral ABC equals to 1. And just copy this expression here. So from this over equation, we derive that the area of pentagon ABCD equals to 1 square units in its size. So I should find out that the area that we are looking for this question, that is the area of the big pentagon ABCDE is equal to 1 square units in size. 1 square units. And again, I should know that the area of this pentagon ABCDE is equal to 1 square units in its size. So we finish with the second question. The next step, I present you the second question. I solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. Actually, the green shape is the green triangle A and B. So we have to find out the area of this green triangle A and B. In the drawing, we have a circle. Chord AB is the diameter of the circle. So that's a known. This is called AB, this is the diameter of this circle, according to what is given as the question. In addition, we know that those two angles are both right angles. Line segment AP equals to 9 units in itself, line segment BQ equals to 4 units in itself. PQ is the tangent to this circle, is point M. Or point M is the point of tendency of tangent PQ with this circle. Again, our task is to find out the area of this green shape, that's actually the green triangle A and B. So, here we can implement rule 7 in our drawing. So, repeat quickly rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. Chord AB is the diameter of the circle. This is peripheral angle ACB that subtends on the diameter of the circle. This is actually chord AB. And therefore, peripheral angle ACB is equal to 90 degrees in its size. So, according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing. Why? Because in our drawing, we have peripheral angle A and B that subtend on the diameter of the circle, that is called AB, and therefore it must be equal to 90 degrees in its size according to rule 7. Write it down, we should follow that peripheral angle A and B equals to 90 degrees in its size according to rule 7. In the next step, we define this angle, the angle PAM as alpha. So, in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, according to the rule that the sum of the angles in an triangle is equal to 180 degrees. PQ is a tangent to the circle at point M. PQ is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PQ at point M here, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is equal to 90 degrees minus alpha, plus this angle that is equal to 90 degrees, plus this missing angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So to now, I have found out that 90 degrees minus alpha plus 90 degrees plus this missing angle, the different angle BMQ. So in total, it must be equal to 180 degrees according to rule 3. So repeat again. The sum of those three angles must be equal to 180 degrees. So 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees, it is 180 degrees. So in total we have here 180 degrees plus the missing angle BMQ minus alpha. This side of the equation. We have 180 degrees plus the missing angle BMQ minus alpha equals to 180 degrees. Here we have 180 degrees on both sides of this equation, so 180 degrees will get cancelled. Also cancel 180 degrees. On this side of the equation we have to only with angle, the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation. And finding again that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ is equal to alpha degrees in its size. So in this small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the three angles of this in this big right triangle A and P are corresponding equal to all the three angles of this small right triangle B and Q, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle APM is similar. This is the sign of similar to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. Again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship is between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side PQ of the small right triangle BMQ. AP equals to 9, according to what is given as the question, over MQ. MQ is the missing side, so leave this it is. it is equal to PM. PM is the missing side, so as it is, over BQ. BQ equals to 4 units in itself, we go into what is given as the question. So in total, we shall find out that 9 over MQ equals to PM over 4. Here we cross multiply this equation, and finally we get that 9 times 4 is 36. So 36 equals to PM times MQ. And again, I should know that PM times MQ equals to 36. In the next step, we define the radius of this circle. This point is point O. So OA is the radius of the circle that we define as R. So OA equals to R. Likewise, OB is also the radius of the circle that is equal to R according to our definition. In the next step, we will join points O and M together by straight line. Point M is the point of tendency of tangent PQ with this circle. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, is equal to R. The radius of OM is equal to R, the radius of M is drawn to point M, that is the point of tendency of tangent PQ with this circle. Whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from point O, that is the center of this circle, we will go perpendicular on side AP. Again, from point O, we will go perpendicular on AP. Luckily, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O inside AP. This point is point L. By doing this construction, we get the big quadrilateral LOMP. So inside the big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is equal to 270 degrees. So 270 degrees plus the size of this fourth mixing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth mixing angle must be equal to 90 degrees in its size. So in quadrilateral LOMP we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be tesseractal, if not a square. So so the big quadrilateral LOMP is rectangle because it has 4 right angles. Quadrilateral LOMP is rectangle according to all 5. The next step, we'll do another construction. That is to say, from point B, we will draw perpendicular on the radius OM. Again, from point B, we will draw perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. When doing this construction, we can do the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 rectangles. Therefore, this 4 pieces must be equal to 90 degrees in its size. So for the other SBQM has 4 rectangles, so therefore it is a rectangle according to all 5. So write it down. In the next step, we focus on this big rectangle LO and P. We know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP must be parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AEP itself must be parallel to the other straight line OM. So if you found out that AP is parallel to OM, write it down. Side AP is parallel to the radius OM. In the next step, we'll copy those two parallel lines AP and OM in a new page, and also the diameter AOB, and we'll implement 150 on the new drawing. So actually, those are the two parallel lines AP and OM. This is the diameter AOB that touches the two parallel lines at points A and B and O. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore must be equal to each other in their sizes according to all 50. So repeat quickly on all 50. According to all 50, corresponding angles between parallel lines are equal to each other. In the following we have line A that is parallel to line B. In addition we have the red line C that cuts the two parallel lines at those 2 points. Those angles alpha and beta are defined as corresponding angles and they are located between these parallel lines A and B, and therefore they must be equal to each other in their sizes. That is to say, alpha equals to beta. We already implemented all 50 in our drawing. Why? Because in our drawing, those two angles are defined as parallel. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM. And as I already said before, therefore they must be equal to each other in their sizes according to all 50. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to all 50. So in conclusion, we found out that this is angle PAO is equal to beta. So this is angle PAO this is equal to beta. And we also found out that angle MOB also equals to beta. So here this is angle MOB that is also equals to beta. So here this right angle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing must be equal to 90 degrees minus beta. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle ALO, this angle equals to beta. This angle equals to 90 degrees, and therefore this first missing angle must be also equal to 90 degrees minus beta according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can join to each other according to angle side angle rule. So we have to prove that the upper right triangle AOL can join to the lower right triangle OSB according to angle side angle rule. And again, we have to prove that the upper right triangle AOL can join to the lower right triangle OSB according to angle side angle rule. So why those two right triangles can join to each other? First of all, those two angles are both equal to beta and therefore they are equal to each other. So here this is angle ALO. in the right triangle, and it is equal to this angle. This is actually angle SOB. In the right triangle OSB. Again, actually found out that angle ALO in the right triangle AOL is equal to angle SOB in the right triangle BOS. They are both equal to beta, and therefore they are equal to each other. In addition, those two sides are also equal to each other. That is to say, side AO of the right triangle ALO is equal to side OSB, to side OB of the right triangle OSB. They are both the area of the circle that is equal to 1, and therefore they are equal to each other. So, on the down, if you hold that side AO in the right triangle ALO is equal to side OB of the right triangle OSB. They are both the area of the circle that is equal to 1, and therefore they are equal to each other. Side AO of the right triangle ALO is equal to side OB of the right triangle OSB. They are both the area of the circle that is equal to 1, and therefore they are equal to each other. And finally, those two sides, they are both equal to 90 degrees minus beta, and therefore they are equal to each other. So here this is angle AOL. The right triangle ALO, and it is equal to this angle, that is actually angle OBS. The right triangle OSB. Okay, again, I should find out that angle AOL in the right triangle AOL is equal to angle OBS in the right triangle OSB. They are both equal to 90 degrees minus alpha, and they are both equal to 90 degrees minus beta. They are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if you prove that those two angles and the side that is included between those two angles, that is R, are in this right triangle ALO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is also R, in the right triangle OSB. And therefore those two right triangles can go into each other according to angle, side, angle, wall. So, if you found out that the right triangle AOL congruent, this is the sign of congruent, to the right triangle OSB, according to angle, side, angle, wall. If we again, we should find out that those two angles and the side that is included between those two angles, this right triangle ALO, are corresponding equal to those two angles, and the side that is included between those two angles in this right triangle OSB. And therefore, those two right triangles can go into each other according to angle, side, angle, wall. And from the fact that those two right triangles can go into each other, we will derive that LO equals to SB. LO equals to SB. This is to say, side LO in the right triangle ALO is equal to side SB in the right triangle OSB. They are equal to each other according to the rule that says that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides LO and SB must be also equal to each other in their lengths. So if we define the length of side LO as x, then the length of side SB must be also equal to x because they are equal to each other. We know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, Side LO must be equal to the opposite side PM. But LO is x, therefore the opposite side PM must be also equal to x units in its length. Likewise, in the small rectangle SBQM, side SB must be also equal to the opposite side MQ. But SB is x, therefore the opposite side MQ must be also equal to x units in its length. Only to rule that the opposite sides of a rectangle are equal to each other. We already found out that PM times MQ equals to 36. And again, according to what we already found out, PM times MQ equals to 36. PM is x, MQ is also x. So total PM times AQ, PM times MQ is x times x, that is 36. X times x equals to 36, x times x is x squared. So x squared equals to 36. Here we'll take a root out of this equation. And finally get that x equals to the square root of 36, 36. So x equals to 6 units in its length. PM is equals to x is equal to 6 units. Likewise, MQ that is also equal to x is equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem on this right small triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evolution of Pythagoras theorem. So in this small right triangle BMQ, BM squared is the square of the hypotenuse is equal to BQ squared plus MQ squared. Which again, in the small right triangle BMQ, according to the Pythagoras theorem, BM squared equals to BQ squared plus MQ squared. BM is the missing side, so we leave it as it is, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So to that we found out that BM squared equals to 16 plus 36. 16 plus 36 is 52. So BM squared equals to 32. Again, 16 plus 36 is 52. So BM squared equals to 52. Here we take out all the equation and finally get that BM equals to the square root of 52 units in its length. side BM is equal to the square root of 52 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle APM. Here by PT is a version of Pythagoras theorem. In the right triangle APM, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, must be equal to AP squared plus PM squared. But again, in the right big triangle APM, according to the Pythagoras theorem, AM squared equals to AP squared plus PM squared. AM is the missing side, so we have to see this, so it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we should find out that AM squared equals to 81 plus 36. 81 plus 36 is 117. So AM squared equals to 117. Here we will take a root out of this equation and get that AM is equal to the square root of 117 units in its length. So here, this is slide AM. This equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape it is actually the right triangle AMB. So we have to find out the area of the green right triangle AMB. So we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this green right triangle AMB will be equal to the base MB times the height MA over 2. And again, the area of the green right triangle AMB, this is actually the area of the green shape, is equal to the base MB times the height MA over 2. We have already found out that MB equals to the square root of 52 units in its length. Times the height AM, that is equal to the square root of 117 units in its length. Divided by 2. So in total, we actually found out that area of the grain pattern AB, the area of the grain shape is equal to the square root of 52 times the square root of 117 over 2. Here we use the algebraic identity. It states that square root of A times square root of B is equal to the square root of A times B. According to this algebraic identity, we get that square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084. This is the square root of 6084 over 2. The square root of 6084 is 78 divided by 2. 78 over 2 is 39. So in total, I found out that the area of the grain shape, that is the area that we are looking for this question, is equal to 39 square units in size. Again, I should found out that the area of this grain shape is equal to 39 square units in size. So, finish with the second question. In the next step, I'll summarize the lecture. We start with the first question, of course. Our task in the first question is to find out the area of this big pentagon ABCD. Say it again. Our task is to find out the area of this big pentagon ABCD. So what is a pentagon? A pentagon is a flat closed shape with 5 straight lines and 5 interrogants. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interrogants, 1, 2, 3, 4, 5. So, in the drawing, we have pentagon ABCDE. In addition, we know that those two angles are both right angles. Side ED equals to side EA equals to side BC. They are all equal to 1 inch in their lengths. DC equals to x and AB equals to 1 minus x. Again, our task is to find out the area of this big pentagon ABCDE. So first of all, we join points A and B together by a straight line. We join points E and C together by a straight line. In the next step, we extended side BA of this pentagon ABCDE. We extended side BA by a straight line in such a way that the extended part AM will be equal to x units in its length. So AM equals to x units in its length. We've only done a construction. BA is one side of the big pentagon ABCD, and therefore it is absolutely a straight line. We extended the straight line BA by a straight line, and you extend the straight line by straight line, the result BM must be also a straight line. So BM is the straight line, so if you measure the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to all three. All three state that the sum of the areas from one side of the straight line is equal to 180 degrees. So each areas we have the upper side of the straight line BM at point A, we have this area that is the right area, plus this missing area. In total the sum of those two areas must be equal to 180 degrees according to all three. Therefore this missing area must be equal to 90 degrees in its size. In the next step we join points C and M together by straight line. By joining points C and M we created the green rectangle EMA. In the next step we prove that those two right green triangles can go into each other according to side angle side rules. That is to say, we prove that the right green triangle EAM can go into the right green triangle, this right green triangle EDC according to side angle side rules. So when those two right green triangles can go into each other. First of all, those two sides are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. So if you prove that those two sides and the angle that is included between those two sides, this right triangle EMA was only equal to those two sides and the angle that is included between those two sides, this right green triangle EDC. And therefore those two right green triangles can go into each other according to side angle side rule. We have two sides and the angle that is included between those two sides in this right triangle EAM of course equal to those two sides and the angle that is included between those two sides in this right triangle EDC. And therefore those two right green triangles can go into each other according to side angle side rule. Okay, again I have to remember that the green right triangle EAM can went, this is the same can went to the right green triangle EDC according to side angle side rule. And from the fact that those two right green triangles can go into each other, we derive two things. First of all, we derive that the areas of those two right green triangles must be equal to each other. Whenever you have two triangles that can go into each other, they must have also the same areas. So the area of this triangle EMA is equal to the area of this triangle EDC. And again, the first thing that we derive from the fact that two right green triangles can go into each other is that they have also the same areas. That is to say, the area of the green right triangle EAM is equal to the area of the green right triangle EDC. And the second thing that we derive from the fact that those two right green triangles can go into each other, we derive that EC equals to EM. That is to say, side EC of the green right triangle EDC is equal to side EM of this green right triangle EAM. EM equals to EC, or EC equals to EM. When those two sides are equal to each other, those two sides are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two green right triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. So EC equals to EM. In the next step, we calculated the area of this line segment MB or side MB. MB in total equals to MA plus MB. And MB equals to MA plus AB. So MB in total equals to MA, that is x, plus AB, that is 1 minus x. So in total, MB equals to x plus 1 minus x. X minus x is 0, so we left only with 1. MB equals to 1 unit in its length. The next step, we prove that this triangle in MEB can go into this triangle EBC according to side rule. This is to say, prove that those two triangles can point to each other according to side rule. So why those two triangles can point to each other? First of all, side AB of triangle MEB is equal to side BC of the triangle ABC. They're both equal to 1 and therefore they are equal to each other. In addition, we just right now found out that ME equals to EC. Again, ME equals to EC. And finally, EB is a common side that belongs to both triangles, so I can write down that EB equals to itself as a common side that belongs to both triangles. So we should find out that all the three sides of this triangle EMB are correspondingly equal to all the three sides of this triangle EBC. And therefore those two triangles can point to each other according to side rule. Okay, again I should find out that the right triangle EMB can point, this is the side of can point to the right triangle EBC according to side rule. And from the fact that those two triangles can point to each other, we derive that they have also the same areas. That is to say, the area of triangle EMB is equal to the area of this triangle EBC. Again, the area of triangle EMB is equal to the area of triangle EBC because they can point to each other. In the next step, we calculated the area of this triangle MEB. We know that the area of a triangle equals to the base of the triangle times the height over 2. So the area of this triangle MEB must be equal to the base MB times the height AE over 2. And again, the area of triangle MEB must be equal to the base MB times the height AE over 2. MB is 1, AE is also 1. MB is 1 and AE is also 1. So total the area of triangle MEB equals to 1 times 1 over 2. 1 times 1 is 1 over 2. So total we should find out that the area of triangle MEB is equal to 1 half square units in its size. So we can write here that the area of triangle EMB is equal to 1 half square units in its size. For this equation, 1 half equals to the area of triangle MEB equals to the area of triangle EBC. Here those two sides are equal to each other. We will derive that the area of triangle EBC is also equal to 1 half square units in its size. Again, the area of triangle EBC is also equal to 1 half square units in its size. In the next step, we focus on this big quadrangle EMBC. What is the area of this big quadrangle EMBC? Actually, the area of this big quadrangle EMBC must be equal to the sum of the areas of the shapes that it consists of. And again, the area of this big quadrangle EMBC must be equal to the sum of the areas of the shapes that it consists of. Actually, the quadrangle EMBC consists of those two triangles. And therefore, the area of quadrangle EMBC must be equal to the sum of the areas of those two triangles that it consists of. So the area of the big quadrangle EMBC must be equal to the area of triangle MEB plus the area of triangle BC. Those are the two shapes that it consists of, and not anymore. So the area of triangle quadrangle EMBC must be equal to the area of triangle MEB, this is equals to 1 half, plus the area of triangle EBC, this is also equals to 1 half. So total the area of the big quadrangle EMBC must be equal to 1 half plus 1 half, this is 1. So the area of quadrangle EMBC equals to 1 half square units in its size. The area of this big quadrangle EMBC is equal to 1 half square units in its size. But we can also look on the big quadrangle EMBC in a different way, and you can definitely see that quadrangle EMBC consists of two other shapes. The big quadrangle EMBC consists this shape that is right triangle EMA and this shape that is quadrangle ABCE. And therefore, the area of the big quadrangle EMBC must be equal to the sum of the two shapes that it consists of. So the area of triangle EMBC that is equal to 1 must be equal to the sum of the two other shapes that it consists of. That is to say, it must be equal to the area of the green triangle EMA plus the area of quadrangle ABCE. And from this long equation, we will derive that 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABC. Those two sides are equal to each other. That is to say, 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABC. Okay. Those two sides are equal to each other. According to our definition, the area of this triangle EMA equals to z squared in size. So you can substitute the green triangle EMA by z, and you get that 1 equals to the area of triangle EMA that is z plus the area of quadrilateral ABC. So if you found out that 1 equals to z plus the area of quadrilateral ABC. Our test is to find out the area of the big pentagon ABCDE. This is the big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, the area of the big pentagon ABCDE must be equal to the sum of the areas of the shapes that it consists of. The big pentagon ABCDE consists of only two shapes and not anymore. The first shape is this green triangle EDC, and the second shape is this quadrilateral ABC. Therefore, in total, the area of the big pentagon ABCD must be equal to the area of this first shape, and this is the area of this green triangle EDC plus the area of the second shape that it consists of. This is actually the area of this quadrilateral ABCE. And again, we shall hold that in total, the area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the green triangle EDC plus the area of quadrilateral ABC. But according to what we already found out, the area of this green triangle EDC is equal to z squared in size. So you can substitute the area of triangle EDC by z. And total we get that the area of quadrilateral ABCD is equal to z plus the area of quadrilateral ABCE. We already found out that z plus the area of quadrilateral ABCE is equal to 1. So we can write that z plus quadrilateral ABC equals to 1. I copy this equation here. Z plus the area of quadrilateral ABC equals to 1. And from this long equation, we will derive that the area of the big pentagon ABCD is equal to 1 squared in size. Again, the area that we are looking for in this equation, that is the area of the big pentagon ABCD, is equal to 1 squared in size. We'll finish with the first question. In the next step, I present you the second question and solve the second. We repeat of the solution of the second question that we have already solved. In the second question, our test was to find out the area of this green shape. The green shape is actually triangle A and B. So we have to find out the area of the green triangle A and B. In the drawing, we have a circle. We know that called AB is the diameter of this circle. We also know that those two angles are both right angles. PQ is the tangent to the circle at point M. We know that AP equals to 9 units in its length, PQ equals to 4 units in its length. Again, our task is to find out the area of this green shape, the area of this green shape is actually triangle A and B. We have to find out the area of triangle A and B. So here we can implement rule 7, y equals the triangle A and B. And subtend the diameter of the circle, and therefore it must be equal to 90 in its size. Then again, rule 7, if you place an angle subtend on the diameter of the circle, then it is equal to 90 degrees inside. In the drawing, we have a circle. AB is the diameter of the circle. This is triangle ACB that subtend on AB, that is the diameter of the circle, therefore it is equal to 90 degrees inside. So according to this rule 7, any triangle that subtends on the diameter of the circle must be equal to 90 degrees inside. In the drawing, we have triangle A and B that subtend on the diameter of the circle, that is called A, and therefore it must be equal to 90 degrees inside according to rule 7. The next step, we find this angle is alpha, so in the big right triangle APM, this angle equals to alpha, this angle equals to 90 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. So, PQ is a tangent to the circle, point M, so PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So originally we have the upper side of the straight line PQ at point M, we have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus this missing angle, this is angle BMQ, total the sum of those three angles must be equal to 180 degrees according to rule 3. So if you follow that 90 degrees minus alpha plus 90 degrees, plus the missing angle BMQ, total the sum of those three angles must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees is 180 degrees, so here 180 degrees plus the missing angle BMQ minus alpha equals to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and left only if the missing angle BMQ minus alpha equals to 0. Here we have that alpha to the equation, if I found out that the missing angle BMQ equals to alpha degrees inside. This is the missing angle BMQ, this equals to alpha degrees inside. So in the small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The next step is that those two right triangles are similar to each other according to angle similar to. That is to say, those two angles are both equal to alpha and therefore not equal to each other. In addition, those two angles are both equal to 90 degrees and therefore not equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore not equal to each other. So if you prove that all the triangles of this big right triangle APL corresponding equal to all the triangles of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similar to one. So if you found that the big triangle APM is similar, this is the sign of similar, to the right triangle BMQ according to angle similar to one. And from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to the side PM of this big right triangle APM or side BQ of this small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9 over MQ. MQ is the missing side, so we leave it as it is, and it equals to PM. PM is the missing side, so we leave it as it is, or BQ. BQ equals to 4. So in total, if you found out that 9 over MQ equals to PM over 4. We have 9 over MQ equals to PM over 4. Here you cross multiply this equation and find out that 9 times 4 is 36, so 36 equals to PM times MQ. In the next step, we find the center of this circle, this point is point O. So OA is the radius of the second that we define as R. OB is also the radius of the second that is equal to R according to our definition. We join points O and M together by a straight line. So point O is the center of the second, point M is the point of the second itself, therefore OM is the radius of the second that is equal to R. Here we can implement rule 1. OM equals OM, the radius of OM is equal to R. The radius of OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to radius MO. If PQ is perpendicular to MO, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point O, we do perpendicular on side AP. Again, from point O, we do perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point A. When doing this construction, we get here quadrilateral LO and P. Quadrilateral LO and P, we have 1, 2, 3 right angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this four faces, and total must be equal to 360 degrees. According to the rule, the sum of the angles in quadrilateral is equal to 360 degrees. And therefore this four faces again must be equal to 90 degrees in its size. So quadrilateral LO and P is 4 angles, and therefore according to 5, quadrilateral LO and P is a rectangle. In the next step, we did another construction, that is to say from point B, we do perpendicular on the radius OM. Again, from point P, we do perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. When doing this construction, we get the small quadrilateral SBQM. Beside the small quadrilateral SBQM, we have 1, 2, 3 rectangles. And therefore this four faces angle must be equal to 90 degrees in its size. And therefore quadrilateral SBQM is a rectangle because it has 4 rectangles. In the next step, we focus on this big rectangle LOMP. We have the rule that says that the opposite sides of a rectangle are parallel to each other. So in rectangle LOMP, side LP must be parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line, that is OM. So if you find out that AP is parallel to OM. AP is parallel to OM. In the next step, we commit the two parallel lines AP and OM, and also the diameter AOB. In the equation, we implemented rule 50, and then we draw it. Those are the two parallel lines AP and OM, and this is the diameter AOB that are coming from the original drawing. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and according to rule 50, corresponding angles between parallel lines are equal to each other. Therefore, those two corresponding angles that are located between the parallel lines AP and OM must be equal to each other according to rule 50. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So if you find out that angle PAO equals to beta, this is angle PAO is equal to beta. Also found out that angle MOB also equals to beta. This is angle MOB is also equal to beta degrees in size. In the next step, we prove that right triangle ALO can go into this right triangle OSB according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, those two sides also equal to each other because they are both the radius of the circle, and therefore they are equal to each other. That is to say, AO equals to OB equals to R. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles in triangle ALO corresponding equal to those two angles and the side that is included between those two angles in the right triangle PHB. Therefore, those two right triangles are congruent to each other according to angle, side angle. So if again, I should follow that the right triangle AOL congruent to the right triangle OSB according to angle, side angle rules. And for the fact that those two right triangles congruent to each other, we derive that LO equals to SB. LO equals to SB according to the rule that corresponding sides in congruent triangles are equal to each other. This is to say those two triangles congruent to each other, and therefore the two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. So if you define the length of LO as x, then the length of SB must be also equal to x because they are equal to each other. You know that the opposite sides of the rectangle are parallel to each other. So in the big rectangle LOMP, side LP must be parallel to the opposite side OM. And LP is parallel to OM according to the rule that the opposite sides of the rectangle are parallel to each other. But LP is part of the straight line AP and is parallel to OM. So if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line MO. So in total, we should follow that AP is parallel to OM. AP is parallel to OM. In the next step, I commit those two parallel lines AP and OM, and also the diameter AOB in the new page, we represent all 50 in the new drawing. Okay, those are the two parallels AP and OM, and this is the diameter AOB that are coming from the original drawing. Those two angles are defined as corresponding angles and are located between the parallels AP and OM, and therefore they must be equal to each other according to Rule 50. Rule 50 says that corresponding angles in congruent triangles are equal to each other. Those two corresponding angles that are located between the parallels AP and OM must be equal to each other and their sizes. So if you find the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to Rule 50. So in total, we should find out that angle PAO equals to beta. This is angle PAO that is equal to beta. And we also found out that angle MOB also equals to beta. This is angle MOB that is also equal to beta degrees in size. So in this triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this quadrant angle must be equal to 90 degrees minus beta according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this quadrant angle must be equal to 90 degrees minus beta according to the circle that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle, side angle rule. This is to say, we prove that the right triangle ANO can go into the right triangle OSB according to angle, side angle rule. So when those two triangles can go into each other, first of all, those two angles are both equal to beta and therefore they are equal to each other. In addition, side AO equals to side OB, they are both the area of the circle and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So if you follow that those two angles and the side that is included between those two angles in this right triangle ANO are corresponding equal to those two angles and the side that is included between those two angles that is side OB and the right triangle OSB. Therefore those two right triangles can go into each other according to angle, side and rule. And for the fact that they can go into each other, we derive that LO equals to SB. LO equals to SB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say LO and SB, must also equal to each other in their lengths. So if you define side LO as x, then side SB must also equal to x because they are equal to each other. So in left hand LO and P, the opposite sides are equal to each other. This is to say LO equals to PM. But LO is x, therefore PM must be also equal to x unit in its length. Likewise, in the small rectangle SB QM, the opposite sides are equal to each other. This is to say side SB is equal to the opposite side MQ. But SB is X, therefore the opposite side MQ must be also equal to X units in its length. We already found out that PM times MQ equals to 36. PM is X, MQ is also X. So PM is X, MQ is X. So the PM times MQ equals to X times X, that is 36. X times X is X squared, so X squared equals to 36. Here we took out all the equation and found out that X equals to the square root of 36, that is 6. So here X equals to 6 and here also X equals to 6. In the next step, we provide the Badaras theorem and this time MBQ. According to the Badaras theorem, this time MBQ, B M squared is the square of the hypotenuse equals to BQ squared plus QM squared. With the small letter BMQ, BM squared is the square of the hypotenuse equals to BQ squared plus MQ squared. BM is the missing side, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So we found out that BM squared equals to 16 plus 36, that is 52. So BM squared equals to 52. Here with the root of this equation, we found out that BM equals to the square root of 52 units in itself. This is answer at BM. This is equals to the square root of 52 units in itself. In the next step, we apply the Badaras theorem on this line APM. According to the Badaras theorem, the right big triangle APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. Considering the right triangle AMP, according to the Badaras theorem, AM squared is the square of the hypotenuse equals to AP squared plus PM squared. AM is the missing side, so limit is it, so it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we have found out that AM squared equals to 81 plus 36, that is 117. Here we took out all the equations, so AM equals to 117. Here we took out all the equations and found out that AM equals to the square root of 117 units in its length. This is like AM equals to the square root of 117 units in its length. Our test is to find out the area of this green shape. The green shape is actually the right green triangle MP. So we have to find out the area of the green right triangle MP. The area of the green right triangle MP must be equal to the base MB times the height MA over 2. So the area of the green shape and the area of the green right triangle MP is equal to the base MB times the height AM over 2. MB is square root of 52 units in itself, and the AM is the square root of 117 units in itself. So again, AMB equals to the square root of 52, MA equals to the square root of 117, and you have to divide it by 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. Therefore, according to this algebraic identity, we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is 684 divided by 2. So the square root of 684 is 78 divided by 2. 78 over 2 is 39. So in total, if you found out that the area of the green shape, that is the area that we are looking for, this question, the area of this green shape is equal to 39 square units inside. Okay, thank you very much.